The proper use of redundancy starts with considering what purpose the redundancy serves in terms of system dependability. The most common use of redundancy is to improve availability. This is often done with a primary system and a standby system, such as a hot standby that is continuously running as a shadow of the primary system. That way, the hot standby system can take over the instant the primary system fails. A point that is often overlooked is that the standby needs to detect that the primary has failed. Detecting many failures is relatively straightforward using heartbeats or detecting system crashes. However, some failures can be much more difficult to diagnose and might be missed by an automatic failover system. This use of ordinary redundancy for failover works pretty well for low criticality systems in which the risk of an occasionally missed failover is more than offset by the high fraction of times that the failover will work properly. That's especially true if a human can step in to trigger the failover if something weird happens. To go further, we'll start with the assumption that components break infrequently and independently enough that we only need to worry about one component breaking at a time rather than multiple concurrent component failures. Even so, any single component can fail in an arbitrarily bad way, which is known as failing active. While some active failures can be relatively benign, it is always possible for any single component to do the worst thing possible for the safety of your system, such as issuing a dangerous control command. While it is always a great idea to have self-checks, built-in self-test, self-diagnostics, and so on, it is impossible to guarantee that these will detect all failures, because, for example, the self-tester itself could be the source of a failure that is causing your system to misbehave. Therefore, any single component is unsafe for life-critical applications or high-SIL mission-critical applications, such as, for example, L33 or L4 systems. Having a standby component does not solve this, because the standby mechanism is solving an availability problem, not a fault detection problem. A different use for redundancy is for fault detection, as shown by the 2 of 2 fail-silent pattern. With this pattern, there are two identical computers called Channel 1 and Channel 2. Each of those identical channels has its own independent set of inputs, and the two channels run identical software and identical computations. The two channels continually cross-check their internal state by, for example, exchanging digests of internal RAM values. They also cross-check their outputs, although in this presentation we will not draw the output arcs explicitly just to try and keep the diagrams simple. The two channels cooperate for producing system outputs. If either channel suffers a fault, the cross-check will detect a mismatch between the internal state or the outputs, and the channels will mutually do a safety shutdown. The net effect is that a component fails silent, meaning that it is either working 100% properly or it does a clean shutdown, but never actually does anything wrong. Because this redundancy is used for cross-checking, it does not help availability. In fact, you can say it hurts availability by shutting down as fast as possible if something goes wrong, but that does provide safety. It is certainly tempting to try to come up with some sort of hybrid failover redundancy and cross-checking combination. For example, one could say you will cross-check until there's a failure, and then use self-diagnosis to figure out which component failed and put the good one in charge. This will probably work some of the time, or even most of the time. But once in a while, you'll hit a case where the self-diagnosis is inconclusive. Both systems will say they're just fine, and then you have to pick perhaps the bad one to be in charge, becoming unsafe. Or the two components will keep fighting over who's broken, and your system will enter limbo where it's neither working nor broken. To be sure, there are some situations in which a hybrid approach is a good idea, but usually such systems have additional redundancy someplace else to take care of problems when the hybrid scheme doesn't really work out.